Hello. Yes, good afternoon. Okay, so if any, yeah, it's 5. Okay. Yes, yes.
Hi, Sushil.
I'm just, yeah, hi. I'm sharing my screen.
Yes.
Yeah, so is it visible? Yeah, is
Yeah,
it visible?
it's visible, but I think the good note should come.
What?
Yeah, now it's visible. Your good note is visible.
Yeah. All right. So if you have any question, okay. So today's lecture 3. Am I audible?
Yes,
Yes,
sir.
you're audible. Yes, you're audible, Sushil.
All right. So let us look at one of the important theorem, most important theorem in complex analysis. So Cauchy's theorem. For rectangular region. Okay. So, of course, as I said last time, I'm not going to refer anywhere in our differential form. So this is the most simplest way to go with Cauchy's theorem. So a rectangular region, as we understand, it is let's say a rectangular region. I'll consider the rectangular region in this form. Let's say this is x equal to a, and this is x equal to b, and let's say y equal to c, and y equal to d. So we have something like this. Yeah. So we have a region like this. So we'll consider the inside as rectangular region. So I sometimes speak about just rectangle or rectangular region. Will always mean the inside. Okay. So the theorem, let's call it 3.1, maybe third lecture. So suppose f is a holomorphic function on this rectangle R, on a neighborhood of R closer, actually on a neighborhood of R closer. So R closer is nothing but z equal to x plus iy, such that a lesser equal to x lesser equal to b, and c lesser equal to y lesser equal to d. All right. So suppose f is a holomorphic function in a neighborhood of this region, this closed set,
Suman, please start recording the lecture.
then integral del r f dz is 0. So del r will be the boundary going in anti-clockwise direction. So the way to consider the direction is the domain should be in your left if you are walking through the curve. So that's how you should get the direction. So domain should lie in the left if you walk through this along the curve. So in this case, this rectangle is the curve, the boundary, and so on this boundary, the integral should be 0. All right. So here I'll neither use any differential form nor will I use any techniques which actually which allows us in differentiating under integral sign. We'll just use some basic method, right? So let me ask you a simple question. It's not about complex analysis. So do you remember the proof of Heine-Borel theorem? Just in case of interval, closed interval.
Usually we use sequential compactness to prove.
Oh, I mean, don't take names. You tell me the techniques, how one does.
So bounded sequence, then use Poisson-Strauss theorem, which will always have a convergent subsequence.
Oh, no. I mean, not that one. Closed and bounded set is compact. Just from the definition. It is
we take a
yeah.
we take a open cover and we divide the interval into half, and
Right. So that is the point. That is the precise point. So you first take the closed interval, divide by half, right? And then suppose you have, you have some portion will have infinite, will not have any finite cover. You divide that again by half, and keep on doing, and make it so small that you can you can actually put that small interval inside one of the open sets, open covers, one of the members of the open cover, and that would actually contradict the assumption. So that's the idea. Even in R2, even in Rn. So even in R2, what will you do? We look at rectangle, and you will divide into 4 parts, and you keep on doing that. So we just use this one only, nothing else. In this case, look at this. The similarity of the method doesn't change much, but in this, the setting is different here. So proof, consider, so define this integral to be IR. Or FDZ, whatever. Now, let's go to next page. We take the, let me draw the rectangle again. All right. So what we would like to do is divide this into 4 rectangles. All right. Now we had this direction, right, in the blue curve. You should, while dividing this one also, you should this divide in such a way, and you take the direction in such a way that this direction, the blue curve, does not change. So here it will go this way, and you go this way, and you go this way, and come back here. So that should be the first one. Call this as R1. And here the direction would be this, go this way, and come back here. So this is R2. And similarly here, you go this way and go this way and go here, and then go here. All right. So this is, call this as R3. And similarly here, you go this way, then you go this way, and you go this way, and then you go this way. You see this one, this curve, this line, and this line is traversed twice, right? And in opposite direction. So in the integration, this, and this will not contribute anything. Is this fine? Yeah? All right. So this one, call this R4. So the first step is to divide this one, and note the following. IR is IR1 plus IR2 plus IR3 plus IR4. All right. So this is equation, let's say equation 1. Now we since there is this summation, we can assume, actually we can, yeah. Well, Well. Actually, we are not assuming. It's basically there exists at least one rectangle Rk such that IRK is greater or equal to 1/4 mod IR. So is this okay? See, IR is the summation of this 4, right? So if all of them should be strictly less than 1/4 IR, then there will be contradiction, right? So let me give a small argument. If IRK is strictly less than 1/4 IR for all k, that means mod IR, which is less or equal to summation over j over k mod I R k equal to 1 to 4 is strictly less than 1/4, right? 1/4 plus 1/4 plus 1/4 plus 1/4 I R, right? Which is nothing but I of R modulus, and this is the contradiction. This gives you the contradiction. So this holds. So we assume R1 is that Rk. Okay. Now we repeat the process. What to get? Well, repeat the process n times to get the rectangles are actually, this is R containing R1, R2, and so on, Rn, right? Such that I of Rn will be modulus will be greater or equal to 1/4 I R n minus 1 and so on, right? So which means it will have 1/4 square I R n minus 2, right? And so on. So this gives you IR n will have greater or equal to 1/4 to the power minus 3 I R n minus 3 and so on, like this. So this is actually greater or equal to 1/4 to the power, 4 to the power 3. What did I write? Yeah, 4 to the power n I R. All right. So we also note that diameter, which is in rectangle nothing but the diagonal, distance of the diagonal, Rn converges to 0 as n tends to infinity. All right. Since Rn is a sequence of nested rectangles, right? Nested sequence of compact sets, and the diameter converges to 0, the intersection of Rn will have just 1 point. It will just be 1 point. Let's call it Z0. Z0 belongs to R. Right? Now we use holomorphicity. So since F is holomorphic in a neighborhood of R closer, there exists delta greater than 0 such that F is holomorphic on a delta neighborhood of Z0, which means mod of Z minus Z0 less than delta. All right. So on delta neighborhood Z0, F will be holomorphic. And since Rn's converging diameter of Rn converges to 0, so for this delta, there will exist an n0 natural number such that Rn will lie in this set. Z in C such that mod of Z minus Z0 less than delta. And this is true for all n greater than n0. All right. Is this clear? Is there any question here?
Sir, repeat the last argument.
Yeah, so Rn converges to, diameter of Rn converges to 0, right?
Yes, sir. Yes.
So whatever delta you take in a, and an intersection is Z0, right? Z0 is in Rn for all n. So that means you take a neighborhood of Z0, your Rn will be inside, right? For large n. Right? That's what we did. Because this intersection is only Z0, and you have this property, right? Which I have not mentioned here, but it was there, right? This one. See, decreasingness. That gives you this. There is nothing complex analysis here. It's topology. Yes.
F is holomorphic in the neighborhood of R bar.
Neighborhood of Z0.
Yeah.
This is the neighborhood of Z0, right? Z0 may lie in the boundary also. So, for example, if Z0 lies here, Z0 may lie here also.
End point.
So that is the reason you need a neighborhood.
Thank you, sir.
Okay. All right. Any other question? Now we'll use holomorphicity and little bit of estimate of holomorphicity. So F is holomorphic, right, at Z0 or in neighborhood of Z0, right? At Z0, while at Z0 one does not say in the neighborhood of Z0. Z0. So in particular, this limit Z tends to Z0, Fz minus Fz0 by Z minus Z0 exists, and this is F prime Z0. All right. So now we use in terms of epsilon delta here. So for every epsilon greater than 0, so we'll use this limit. We'll unfold this limit in terms of epsilon and delta. All right. So for every epsilon greater than 0, there exists, let's say, delta tilde. We can take delta tilde smaller than delta, such that mod of Fz minus Fz0 by Z minus Z0 minus f prime z naught is less than epsilon. This implies mod of fz minus fz naught minus z naught times f prime z naught is less than epsilon times mod z minus z naught. Right? Call this 2. All right. So this is important. And what is this delta? Such that this z minus z naught less than delta tilde. So we can take delta tilde less than delta. All right. Now note few things. We note that the integration on del Rn dz, this is 0, right? Because one has a primitive, which we did last time, which you have shown, right? We also know this is a closed curve and one has a primitive, the function 1. Z dz is also 0. Right? So in this case, primitive exists for the integrand. Okay. Now look at IRN. This is nothing but integration del Rn f z dz. And this I can, since we have this 2, we can add and subtract few things. We can add few things rather. So which means this one del Rn fz minus fz naught, which is a constant, minus z naught times f prime z naught. And then there is, sorry, and there is this dz. All right. So note, what did we do? This is constant. So integration del Rn 1 dz, which means 0 here. And here, see z f prime z naught. F prime z naught is again, this is a constant. So it comes as integration z dz, which is 0 here. And z naught f prime z naught, which is both of them are constant. So it boils down to here. So integration is 0. So subtracting these things does not actually contribute anything to the integration. All right. Now let's make the estimate. IRN less or equal to integration del Rn mod fz minus fz naught minus z naught times f prime z naught mod dz. All right. Now this one we have estimate 2. So this one is less or equal to integration del Rn epsilon times mod z minus z naught mod dz. All right. Is this fine till now?
Yeah, yes, sir.
All right. Now what you need to know is what is this? Right? So this is nothing but less or equal to the diameter of the rectangle Rn, right? So this is now what we have, IRN mod is less or equal to epsilon comes out, and then mod of z minus z naught, this part is dominated by the diameter of Rn. So let's make it diameter of Rn, and you have integration del Rn mod dz. And what is this? This is length of the curve del Rn, which is just the perimeter of the rectangle. All right. So this is epsilon diameter of Rn and length of del Rn. All right. Let's call this 3. Fine. Now we have something like maybe this one. I gave some number, right? Yeah, this is 1. Let's call it 1a. Let's call it 1a. So this 1a will be needed now. From the inequality 1a, we have see 1 over 4 to the power n IR. That was there, which was lesser or equal to I Rn. This was the inequality. This was the inequality 1a. This one, right? So let us check. Yeah, here it is. See. So, and then we use here IRN is lesser or equal to epsilon times diameter of Rn times L del Rn. Now this implies, so call this 4. Now we have this relation diameter of Rn. Since we are dividing always by half, so diameter of Rn will be 1 over 2 to the power n diameter of R. Similarly, the diameter, the length L del Rn will be 1 over 2 to the power n diameter. Sorry, not diameter in this case, it is length L of R, right? We are just looking at the perimeter here, A of del R. Now from 4, we have mod I R is less or equal to epsilon times C 1 over 2 to the power n and 1 over 2 to the power n, that will be 1 over 4 to the power n, which will, so this 1 over 2 to the power n, this 1 over 2 to the power n cancels with this one. All right, if you put here and here, so this one will be the diameter of R and then length of del R. All right, but see here epsilon was arbitrarily chosen, so the integration has to be 0, right? Since epsilon greater than 0 was chosen arbitrarily, integration which is just IR is equal to 0. Yeah, so proof completes. So is this fine? Any question in the proof? So this is the basic version of Cauchy's theorem, whose proof is very, very simple. Does not use much except this the standard technique which we use in proof of universal theorem. Nothing else. Yeah. So any question here?
Sir, in case of choosing rectangular region,
Yes.
can we choose some circular region kind of thing?
Yeah, I'll come to that. Yeah, you can do that, but this method, this works for triangle as well. But in case of just Rn, you cannot just divide, right? So there will be the problem of division. So rectangle or triangle would work very easily. So for example, for triangle, what you would like to do for triangle? For triangular region. Triangle. You would just divide like this, like this, like this. Divide like this, like this, like this, and go on. All right? So go on doing this. Like this. So and use the same method. So instead of this 2 to the power n, there will be some power of 3. 3 or 4. Yeah, actually 4. 1 over 4 to the power n.
The proof of the theorem is true if you take the function is holomorphic on the open rectangle and defined on the boundary.
No, you need a neighborhood of the closed rectangle where f is holomorphic. Right? As I mentioned earlier, that your z0, the point can be in the boundary point.
Actually, function is defined holomorphic on the closed rectangle. That's why R closure is also same as R because it is closed and bounded. Our taken rectangle is closed and bounded.
Yeah. So but what is the assumption? So assumption is a neighborhood of R closure.
Okay.
So this neighborhood is very much important.
Okay.
For example, this z0 if lies in the boundary, you need a neighborhood here,
Okay.
but it is holomorphic.
Thank you.
Right? Okay.
Right.
All right. So this nice technique was developed by Gursat, and the point is, what was the definition of holomorphicity you have chosen? You have seen. Yeah. What was the definition? Did you assume continuously differentiable?
No, differentiable at open set.
No. Did you assume the derivative continuous?
No.
Do you remember that? Are you sure you did not assume the continuity of the derivative?
No, we did not assume.
And still you can do. How do you prove Cauchy-Riemann equation without knowing if the derivative is not continuous?
We took the derivative from two directions.
Yeah, you took the derivative for two direction, but what would be the converse? So go back and see, you actually need the continuity of the derivative. You cannot actually remove continuity of the derivative until this theorem. Here we did not use, in the holomorphicity we have just used what? This limit. The existence of this limit. See, we did not use continuity anywhere. Right? So go back and check that you must have somewhere assumed the continuity of the derivative. And here, see, we never used this one. So hence, this was the observation Gursat made, and he concluded that, or she, whatever, concluded that the derivative, which in the definition of holomorphicity, the continuity of the derivatives which we assume is actually redundant, comes from here. How you will see, but this is the main thing. How you will see a little bit later. We need some more machinery to build. After that, you will see. All right. So go back and check, where did you assume this continuity of the derivative? So let us prove generalization of the previous one. So this is another theorem. So we'll use this one today itself. So let's call it star. Let R be a rectangular region and F is holomorphic in a neighborhood of R closure except at one point, let's say zeta in R. So it's not holomorphic at one point. Okay. Suppose limit z tends to zeta, z minus zeta, fz is 0. Then integration del R, the boundary fz dz is 0. So you see, we actually removed the assumption of holomorphicity at one point. So you can do it for finitely many points also. All right, this is the statement clear? But we had to incorporate this one with a limit. And this limit perhaps you will see later as well.
Sir, is there any specialty to take that limit to be 0?
Yeah. Yes. Later when you see the singularity, this limit will say that
Removable singularity. It will,
yeah. Right?
Yes.
So
using removable singularity thing, this is obvious, right? We should have one analytic function which is same as fz, except at the point z0.
Right.
And integral for that function will be 0 by this previous theorem.
Right. Exactly. But actually, we are not telling about the removable singularity as you defined, right? If you take this limit, then you have to show something.
Okay.
Right?
Yes.
So there exists a holomorphic function, that part is required.
Yes.
Right? And this is how we would show this is holomorphic by Morera's theorem. All right?
Yes.
Circular argument. So this is the basic one. So this showing integral 0, on here it is just, I use rectangle, but you can do it with triangle also. And that gives you later on by Morera's theorem holomorphicity. Okay? All right. So let us look at a proof of this one, a brief proof. So proof is not very difficult. So rectangular region I will consider as before. And what you need to do, suppose zeta is this point, and you have to divide. So look at a small square first. Small square around the point zeta. So this doesn't look like a square, but let us assume this square such that zeta lies in the bisector of this. So let's call this point is zeta. So it is bisector of this in the middle. And then you then what you would like to do is we just divide this one in terms of rectangles. All right. So like this, like this, like this, like this. Now all other rectangles, since f will be holomorphic, f is holomorphic, so it doesn't contribute to the integral. So only this part, only this part remains. So only this part, this square can contribute to the integral. All right. Other things in this or here, function f is holomorphic in a neighborhood of these things. So by previous theorem, all these rectangles, this, all these rectangles, the integral vanishes. And by previous argument, we can actually this integral can be summed as boundary of each of the rectangles here, right? By the previous argument in the proof of previous theorem. Okay, so this is the idea. First you get a square and then make other rectangles, and there it will not contribute anything. All right. So and then note. So we note. Call this square. Let's say R naught. Note that integration del R f dz is nothing but integration del R naught f dz, right? The other rectangle does not matter. All right. So next one, we what we have is limit z tends to, we have by assumption limit z tends to zeta, z minus zeta, fz is 0. Now again we look at in epsilon delta form. So for every epsilon greater than 0, there exists delta greater than 0 such that mod z minus zeta less than delta implies mod z minus zeta fz less than epsilon. So that implies mod of fz is less than epsilon by mod z minus zeta. All right, is this clear? Now if required, divide the square R naught further if required and assume R naught closure lies in z in C such that mod z minus zeta less than delta, just like before, right? So here this one we can divide further and further, keeping this zeta to be in the midpoint, right? And make it smaller and smaller so that this holds. All right. All right. Now, once this is there, now we'll estimate the integral, right? So we will estimate this f digit modulus, right? So less or equal to integration del r naught mod f z mod dz, right? So this is less or equal to mod f z is nothing but this one. So this epsilon comes from here, and then del r naught mod dz by z minus zeta. All right. Now this was a tutorial exercise. Have you done it? How does this this integral bounded by what? Do you remember there was exercise in the tutorial? At least what I circulated that in those problems. So if you have not done it, so do that. So I put it as exercise. It is there in the tutorial. Del r naught d mod dz by z minus zeta is less than 8. So now then this continue the proof. Yeah, so continue the proof. So from now on, so this will be less or equal to 8 epsilon. And since epsilon was chosen arbitrarily, integration del r f dz is 0. Del r naught f dz is 0, and this implies integration del r f dz is 0. All right. Any question here?
Sir, can we have that point theta in the boundary, sir?
No, because we assumed in the very beginning that in the assumption of the theorem, zeta is in R. Right? R is the
Okay.
region. Yeah. R closer is the closer of the region.
Okay. Thank you, sir. Thank you.
Okay. Okay. So by the way, what is the problematic point should not lie in the curve. That should be the first point to note. I will see later on all those. So now let's look at the theorem for circle. So did I what did I give the number of the theorems? Maybe I put a 3.21 here. So let me, instead of star, I put 3.2. So instead of star, let me put it 3.2, and then here 3.3. So let f be a holomorphic function in an open disk D, then integration over gamma f dz is 0 for every closed curve gamma in D. See, we have changed statement a little bit, right? So previously gamma was just the boundary of the rectangles, right? Now here it says that in any closed curve it works. All right. So the idea, so when there is a statement like this for any closed curve and integration is 0, you need a primitive. So that is how to start with. So proof, we need to show there exists a primitive of f on D. This is what it is required. Now, how do you prove such thing? Right? How do you prove such thing? Well, let's draw. Picture is good. So you fix a point x naught y naught. X naught plus I y naught. So this is nothing but z naught. And you consider a point z here, which is x plus iy. And you look at first this horizontal and then vertical, right? This is your curve gamma. So you define, so this you take gamma and you try to define the primitive that we did last time, as we did last time. So define fz to be integration over gamma fz dz. If z was a point there, so fw dw. All right. Now, is it well defined, first of all? Well, here you go this way. This is actually constant, and this part depends on y. So here you recall the theorem, path independent theorem, which we proved yesterday. That from here you will get this del f by del y is I f z. So looking at this vertical line. So similarly, you could consider first vertical and then go along horizontal, right? So this is, let's say, gamma tilde, right? And what is this? You see, by previous theorem, integration on this rectangle is 0, right? So integration gamma f dz or dw is equal to integration gamma tilde f dw, right? By theorem 3.1. All right. And from this part we get, it depends on the endpoint, depends on ax actually. So del f here, del f by del x would be, you need to calculate if you are a little confused here. So I'll invite you to compute this. This will be f of jet. Now what is this? This means actually this to, let me go back to previous one. Yeah, here. So this two means that there exists a primitive. This two means there exists a primitive. So basically, yeah, right. So this part. So this two means this, there exists a primitive like this. So it would come from this kind of computation which I would invite you to do. And so this would imply actually, so this two implies if satisfies Cauchy-Riemann equation. So maybe we call it star and double star and double star imply that F satisfies CR equations. That's what I showed you. And this implies F has a primitive in D. And then this would imply integration over gamma F dz is 0 for every closed curve in D. Is this fine? Since it is last component is vertical, so you will look at that one. So that one actually you are taking derivative with respect to y. And similarly here, last component is horizontal, you are taking derivative with respect to x. All right. So that's all about this. Similarly, you can do it for ellipsoid, half space. So remark, you can.
Sir,
Yes.
you are joining those 2 points by just 2-line segment.
In a circle you can do it, or inside the disk you can do it.
Okay, only 2.
Yeah. Well, if you need more, that also not a problem, because on the rectangles, integration is 0.
Okay, yes, okay.
Right? Yeah. So in fact, for this circle, you can actually go with 2, but yeah. But you actually, if you need more, no problem. So you can follow the same procedure. For ellipse, half spaces, and so on. And you can modify a little bit here. The argument here, you can modify a little bit here to get star domains, star set domains. Yeah, I'm not going to go into these things. All right. So next, let's come to the next topic, the winding number. So winding number roughly means, so actually winding number is a precise way. It is precise way to find how many times a curve moves or winds around a point. Well, before going into defining this one, let's look at a small lemma. So this you already know, I think everybody knows it, but let me state it. I'm not going to prove, but let me state it. Suppose gamma is a piecewise smooth curve in C which does not pass through the point, let's say the point A, then integration over gamma dz by z minus A is equal to 2m pi I for some m in z. All right. So this you perhaps know, right? The point is you cannot prove it directly. You just need a trick. So maybe one idea. So proof. So it would be exercise, but the point is define GT to be integration. So if gamma is from alpha beta to C, so then you define GT to be from alpha to T gamma prime S by gamma S minus A ts. Okay. So GT will be differentiable, and you saw that GT is constant actually. Well, yeah. So no, you don't show that GT. Yeah, you saw GT is constant, but you some way not GT is constant. Actually, you will show that e to the power minus GT gamma t minus A is constant, right? So which means the derivative is 0, which means ddt of the whole thing is 0. So that this is an exercise. Now then exponential property will give you this. So complete exercise, complete the proof. All right. So you need this. You need to prove this lemma before defining what is called winding number, because we will define winding number in this way. Though one can define winding number using the argument function, but this is the easiest way to define. So definition: the winding number of a curve of a piecewise smooth curve gamma with respect to a point A. Point A is defined as follows: eta gamma A is defined as 1 over 2 pi I integration over gamma dz by z minus a, right? So that's what I was pointing out, that we need to define this in terms of this integral. All right. So this is winding number, and the previous one lemma says that it is always an integer. It may be negative. So you can look at few example. For example, let's look at this one. Gamma t is a plus r e to the power I n t. T belongs to 0 to 2 pi. Right? What will be the winding number of gamma? A
Yeah.
n, right? You just compute. So you can look at one more thing, which is well, here actually this you can yeah. So example 2, look at gamma t as rt e to the power it. T belongs to 0 to 2 pi. Rt is always greater than 0. Greater than 0. And gamma of 0 is gamma of 2 pi. So this is making things closed. So you have, let's say, if this is coordinate system, xy, so you have some curve like this. Like this. General curve. We don't know how R is moving. It's just continuous. This was smooth as well. So find. So from picture it is very clear, but you can actually you can show that the winding number of gamma z naught, so z naught is inside here, is 1, and gamma, let's say w naught lies outside, it is 0. Oh, well, for this, showing this one, you actually need some properties. So we will now state and prove few properties. So you might need some of the properties for this computation. All right. So few properties. Few properties of the winding number. So first one is winding number of minus gamma at A is nothing but minus of winding number of gamma with respect to A. The proof is very clear. We have done the integral. So this is nothing but integration over minus gamma dz by z minus A, which is, we already know that minus of integral gamma dz by z minus A, right? For every function we know. Hence this proof. 2. So if gamma lies inside a disk D, then eta of gamma z equal to 0 for all z in C minus D. All right. So which picture is as follows. So So this is a disk, and gamma lies inside of an open disk. So maybe inside of an open disk, right? So this part, you basically you need to, how do you consider these things? You need to look at the complement, and this complement will be containing infinity. There will be only one component. Gamma will be closed and bounded, so it will not. So 1 over z minus z naught will be holomorphic if it lies outside. So that part, and then you will see that inside, use Cauchy's theorem on disk, right? That would give you integration 0. Right? If you z naught lies here, then look at 1 over z minus z naught, and this will be holomorphic in D. And then use Cauchy's theorem. All right, is this clear?
Yes, sir.
So third one. So third one is the first one. The first property is well. Let me put it in this way. So the winding number is constant in each of the connected components of C minus gamma. So there are two ways to prove it. One way is, there might be more, but I know two ways. One is to prove, so first way to prove that z goes to eta z comma z is continuous. And then, of course, in a connected component, this is integer, so it should be constant. Second way, it looks a little bit more interesting to me, so let me sketch briefly what the second way is. So suppose second way is as follows. So suppose this is your gamma going this way, this way, this way, this way. And suppose A and B are 2 points such that the line joining A and B does not intersect gamma. So it lies in a connected component, means it lies in a connected path component. So you can look at near a point A, B near a point A and close enough, and you can look at the straight line such that the straight line does not intersect gamma. So this is a very nice argument. So suppose A, B are 2 points such that the line joining A and B, let's call it AB, does not intersect gamma. All right. Now consider the function. So fz to be z minus A by z minus B. Right? This is a very nice function. And you note that the image of C minus the line joining A B lies in C minus Z such that Z is less or equal to 0. So which means this lies in this part, right? So this image lies in this part. So which means, have you seen branch of logarithm?
Yes, sir.
Okay. So see, you have branch of logarithm for this function. So there exists a holomorphic branch of logarithm log f. Now this implies this integration, integration log f prime or log of f whole prime z dz over gamma is 0, right? Because log f is the primitive. So which means this is nothing but 1 over z minus a minus 1 over z minus b dz equal to 0. This implies index of gamma, the winding number of gamma with respect to A is equal to winding number of gamma with respect to B. So this is very nice argument. Yeah, so what you need to check is this one, this part. So this part I'll just keep as an exercise. The image lies here. So this is a very simple function. All right. Okay, so what's next? So maybe I have 10 minutes, so let me prove Cauchy's integral formula. This would be, or maybe let me give you an exercise about the index, or maybe another example first. Example of the winding number. So consider gamma t to be e to the power minus it, t in 0 to 2 pi, right? So what would be the index of gamma at 0? Winding number of gamma at 0 or with respect to 0?
1?
Is it 1?
Minus.
Yeah,
No, yes, minus 1.
minus 1. It's an exercise. This is a useful exercise. So please solve it. So suppose gamma is a piecewise smooth curve in an open set omega, and f from omega to c holomorphic function. Assume z0 does not lie in the graph of, the curve f compose gamma. Then show that integral, maybe we go to the next page. Show that the winding number of f compose gamma z0 can be given in terms of integral formula like this: f prime z by fz minus z0 dz. Okay, so this is you try to make a change of variable. All right. So next is Cauchy integral formula. So theorem in 3.4. Let F be holomorphic in an open disk D and gamma be a closed piecewise smooth curve in D. For any point Z not in the trace of gamma, we have the following equality. One over 2 pi I integral over gamma fw by w minus z dw, where gamma this z is the winding number of gamma with respect to z. All right. So if it is simple closed curve, it would be, I mean, 1 and points inside, it will be just fz is 1 over 2 pi I integration fz by. So suppose this part is, this is 1. So for example, if you look at a disk here, sorry, disk here, and look at a curve inside here, a small disk. Now, so this, if this is gamma, then the points here z, this winding number will be 1. So in this case, winding number will be 1, and this would be 1 then, and then fz will be this one. So this is the standard form of Cauchy integral formula, which actually uses many places. Okay, but here the proof is very simple. We'll use a theorem proved earlier. So proof: consider the function fw defined as fw minus fz by w minus z by w not equal to z, and f prime z by w equal to z, right? So f is continuous, capital F is continuous, but you don't know whether it is holomorphic, right? But note that limit w tends to z, w minus z, capital Fw is 0, right? So this limit, remember? Yeah. So this plays an important role here. So where did I prove it? Yeah, here. Then you have this 0. So there I have taken just rectangle, but one can actually do that one for any closed curve inside the disk. So that can be that you can look at as an exercise. So once you can do with rectangles, you can do with any curve inside this, just as you do before. So hence, by theorem. So that theorem is a generalization of whatever we proved. That was, I think, 3.2, actually a generalization will be needed. So after we prove the Cauchy's theorem for disk, any curve in the disk, then you can do the same way. So that will get you obtain integration over gamma capital FW dW is 0. Hence this would be integration over gamma FW minus FZ by W minus Z dW equal to 0. This implies FZ integration over gamma dW by W minus Z is equal to integration over gamma FW by W minus Z dW, right? So this part gives you the index. So eta gamma Z Fz is equal to, well, you need 1 over 2 pi I. So this 1 over 2 pi I comes integration over gamma Fw by W minus Z dW, right? So this proves the Cauchy integral formula. Now this can be used to prove that any holomorphic function has path series representation, and hence a path has actually completed. So once you have path series and you have Cauchy-Riemann equations, you have limit as h tends to limit of quotient, and you have Cauchy integral formula. All the things equivalent. That actually this showing that this having this one implies that f has a path series expansion would actually do that. So this is a very nice application of Cauchy integral formula, and this is definitely crucial. Okay, so I will stop here, and you ask if you have a question.
Any questions?
Yes.
Hello. Hello.
Yeah, please ask.
Sir, is this connected to fundamental group, sir?
Well, it is not exactly connected with fundamental group, but of course it is connected. But this index is actually a non-trivial member from homology group, which is the commutator, or just I mean, after making this making the group commutative fundamental group, that is called the first homology group. So this is a member when there is a non-trivial winding number that contributes to some things in the homology group and hence something in the fundamental group. So these are of course connected. We will see in the last lecture that if the fundamental group vanishes, which means that domain is simply connected, we will have this vanishes, and you will see that there are also, for those kind of domains where fundamental group vanishes, you have Cauchy's integral formula, Cauchy's theorem actually, and hence integral. So homotopy form of Cauchy's theorem we'll do next time. Yeah, so complex analysis is deeply connected with
actually,
yes.
okay. Sir, actually, I didn't understand one point. Sir, you told me that you told us that if we have a disk, then any 2 point can be connected by 2 lines. Sir, can we draw first vertical and horizontal, and also horizontal and vertical? I didn't understand both. How can both exist, sir? One should exist, I understand, but how can both?
So see, you have what did I write? Yeah, here, right?
Yes, sir.
So the point is, well, you, of course, here I go with two things, right? So if you are so first you want first horizontal or first vertical, right? Whatever you wish. So maybe if you are here,
yes,
if you are here, then you cannot go actually first vertical, right? If you are right here,
yes,
so there is this kind of problem. So if your point here, you can't. If you go horizontal and you one point here, then you cannot go horizontal first and vertical there. True, but
yes,
it does not matter horizontal how many horizontal you go. Basically, what matters is the last component. What matters is the last component.
yes.
Here, for the drawing purposes, I have taken this horizontal and vertical to get one rectangle. You might get multiple rectangles. Then the integral of each of the rectangle will be 0. Boundary of each of the rectangle will be 0. So what would actually really important is that the last one would be horizontal and one would be vertical. So you can go through a polygonal path whose sides are parallel to axis, but one last component would be last side should be parallel to y, other should be parallel to x-axis. That is good enough. So does that answer your question?
Yes.
Okay. So any other question?
Yes, sir. Sir, it will have only finite sides, sir. That kind of vertical and horizontal.
Yeah, because it is compact. No, you cannot go
Because
finite.
if it is on the yes.
If it is on the no, for compactness you will have only
Sir,
finite.
if it is on the diameter.
Mm-hmm.
Yes. I is come.
Actually,
Yes, sir.
Yeah, it will come. That will be not a problem. Any other question?
So if there are no questions, let us thank Professor Sushil Gorai for very interesting proofs and very simple and very interesting proofs. So we have one more lecture by Professor Sushil Gorai on tomorrow.
Yeah.
Hello.
Yeah, we'll meet tomorrow
Sir,
at 5
actually,
o'clock. Yeah.
Yes.
Yeah, please proceed.
Hello.
Rohit.
Sir,
Yeah.
actually, sir, if we take diameter,
Mm-hmm.
sir, this means that we are taking in point in the interior, sir.
Yeah.
That's
So
why
that
we
was
take.
the beginning, right?
Okay, sir.
That was
Convinced.
the beginning. So you,
Yes, sir. Yes, sir. If we take on the
define-
boundary, we cannot get.
So you actually define this function f on the disk, inside the disk. That would be good enough.
Okay. Thank you, sir.
Okay. Yeah, so let me start presenting.
Yeah.
Yeah, maybe I'll share a few exercises by tomorrow morning. So there will be tutorial tomorrow, is it?
Yes, yes. There is no tutorial, but in case you want, you can arrange.
Oh no, I don't want anything else extra. So in the next tutorial, okay, on Friday next. Okay, so I'll submit. I'll send you a few problems which can be discussed next time.
Okay, thank you, Professor Sushil. And thank you, one and all.
Thank you. Yeah, thank you very much. Okay, see you tomorrow.
Yeah, see you tomorrow.
Okay.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you.
Someone, please tell me, Suman.